Okay, so we're going to look at how rulers are inefficient in the sense that they include more markings than they strictly need. So for example here, we've got a standard 15 centimetre ruler contains 16 markings, and you can measure any distance between 1 and 15 centimetres using that ruler. But we can do the same with this ruler, which has only got 7 markings, and here you can measure 1 centimetre between 0 and 1, you can measure 2 between 1 and 3, 3 between 3 and 6, 4 between 6 and 10, and you can check that this will work for all distances between 1 and 15, which goes between 0 and 15, like that. So why would we bother to do this? Because, first of all, it makes the ruler much easier to use if we have all of these extra markings, and second of all, it's not that difficult to add those extra markings. Well, it turns out there's a really neat application of this idea in astronomy, where astronomers will use a process called interferometry, where they have telescopes in different locations a certain distance apart, and they'll measure the differences between readings on these different telescopes. So you can imagine these as being like your different markings on the ruler. And here it makes sense that you don't want to have to build a load of extra telescopes that you don't strictly need, because here, if you have them in this sort of arrangement where it's more efficient, you can use fewer telescopes to extract more information because you get more of a variety of distances between them. So now that we've seen very briefly an application of this, we'll look at some of the maths behind how we can choose such an arrangement which optimises the number of distances between all of your different markings on your ruler. So turns out to actually be quite a difficult problem to solve in general, and to solve for an optimal solution. But in this video we'll have a look at a solution which is quite good and quite simple, and then we'll explore at the end how close this is to being an optimal solution. So just to build an intuition behind the idea, we'll start with an example where we want to be able to measure, let's say, 100 centimetres, and every distance between 1 and 100 centimetres on our ruler. So the standard way to do this would be like our classic example here, where you'd go from 0 all the way up to 100, so you'd have 101 markings. But there's a really quick, nice way of doing this that helps us to reduce this all the way down to 52, which would be to include 0, 1, 2, all the way up to, you'd have 48, 49, 50, but then skip everything from 50 up to 100. So here you can measure any distance between 1 and 50 just by going from 0 to that number. Then if you want to measure 51, you can go backwards from 100 to 49. If you want to measure 52, you can go from 100 to 48, and so on all the way down to 100 to 1 gives us 99, and 100 to 0 gives us 100. So this gives us a way of measuring every distance between 1 and 100 using only 52 markings. But we can actually improve on this even more. So let's imagine instead of going up to 50, we'll go up to just 25. So we'll have 0, 1, we'll go all the way up to 23, 24, 25. Then we'll have 50, 75, and 100. So to measure all your distances between 1 and 25, you can just go from 0 to 1, 0 to 2, and so on up to 25. Then if we want to measure something from 26 up to 50, we measure backwards from 50 now. So we can do 26 from 50 down to 24. We could do 27 from 50 down to 23, and so on all the way up to 50. You go from 50 down to 0. So we've measured everything from 0 to 50. Then you can measure anything from 51 up to 75 by counting backwards from 75. So we could go 75 down to 24 gives us 51. 75 down to 23 gives us 52, and so on all the way up to 75. Then for everything from 76 upwards, we can measure backwards from 100. So 100 down to 24 gives us 76, and so on all the way up to 100 down to 0 gives us 100. So here we can measure every distance between 1 and 100 again, using from 0 to 24 is 25 plus another 4 here, so we're down to 29 markings here. But we can actually get rid of the 25 here, because we can measure everything from 0 up to 24 just going from 0, and we can measure 25, for example, just going from 50 up to 75. Then we can still measure everything going backwards now, so we get 26 going from 50 down to 24, we get 51 going from 75 down to 24, and we get 76 going from 100 down to 24 like this. We don't actually need the 25, which means we can reduce this now to 28 total markings to still measure 100 centimetres. And we can explore this further and actually improve on this even more. So let's now, instead of splitting it up into 50 or 25, we'll split up into 10. So we'll go 8, 9, and we'll skip 10. As we'll see, we won't actually need 10, like how we didn't need 25 there. Then we'll go to 20, 30, so going up in 10s up to 90, and finally 100. So you can see, just like before, you can measure everything from 0 to 9, just starting at 0, then going along to that number. We could get 10, for example, between 20 and 30. Then we can get 11, going from 20 down to 9, 12 from 20 down to 8, and so on up to 20, going from 20 down to 100. Then we can get everything between 21 and 30, measuring back from 30. We'd get everything from 31 up to 40 by measuring backwards from 40, and so on, like this, all the way up to 100. So here we've got, between 0 and 9, we've got 10 markings, and then from 20 up to 100, we've got 9 markings. So we can actually measure now, using only 19 markings, we can measure every distance between 1 and 100 centimetres. So if we explore this even further, so instead of splitting this up into 10s, let's split this up into 5s just to see what happens. So we'd have 0, 1, 2, 3, 4, we'd skip 5 like before, we'd have 10, 15, going up in our 5 times tables like this, until we get to 95 and finally 100. So just like before, we can measure every distance from 0 up to 4 here, then we can measure 5, for example, between 10 and 15, then from 6 up to 10, we measure back from 10. From 11 up to 15, we measure backwards from 15. From 16 up to 20, we measure backwards from 20, and so on. So you can see this also works. But unfortunately here, we've got, first of all, we've got 5 here, and then we've actually got 19 markings now. So we're up to 24 total markings. So something's gone wrong here, that somehow splitting up into 10s rather than 5s gave us fewer markings. So we'll have an explore, now that we've built some intuition, into how to optimise this solution and generalise this before finally looking at how we can compare this to an optimal solution. Now, if we want to understand why splitting up into multiples of 10 gives us the best possible solution for our ruler measuring up to 100 centimetres, we can look at the slightly more general picture of splitting this up into, first of all, you start with n markings, then we have going up in our multiples of n like this, where n is a factor of 100. So we tried this with n is 50, n is 25, 10, and also 5, and we saw that 10 seemed to give the best solution. So if we just look at this more general picture with n, how many markings have we got? Well, first of all, going from 0 up to n minus 1 gives us n markings. But then we've also got our n times tables all the way up to 100. So this is essentially how many times does n go into 100, but we don't actually include n itself here. So this will be 100 divided by n, but then minus 1. So here you can see we've got n, and then we've got 100 divided by n minus 1 will give us our total number of markings here. And if we want to understand why n is 10 seems to give us the best possible solution, we can think about the function. Let's say y equals x plus 100 over x minus 1, like this. So we've just replaced our n by an x. Then we can use a bit of calculus to show that 10 will give us the smallest possible value here. So when we differentiate this, we get that our dy dx is 1 minus 100 over x squared. And if we want this to be equal to 0, you can see this takes place when x is going to be 10 or negative 10, but that wouldn't make sense for our problem. And using a bit more calculus, we can actually show that this is a minimum point. So I'll just draw a quick sketch of what our graph would look like. You'll see that we get a minimum point when x is 10 here. So you can see that this really does minimise the value of y, or minimises the total number of markings. So to give us a rough idea then of why 10 seems to be our best possible number to choose, for this example going up to 100, it's essentially can be done using calculus like this. And we can extend this argument further. Let's say that we're going to have k total markings are needed. So replace our 100 by just some integer k. Then we're looking at y equals x plus k over x minus 1, just replacing our 100 by k. And once again, we'll look at differentiating this. So we find the derivative is going to be 1 minus k over x squared. And if we set this equal to 0 to find our minimum point, you see this happens when x is equal to the square root of k. And again, it wouldn't make sense for x to be negative here. So once again, we could draw this out, use a bit more calculus to show that this is indeed a minimum point when x is the square root of k. But of course, this example worked really nicely because we got x is 10, which is actually a factor of 100 and is also an integer. But this works because 100 is a square number. So if k wasn't a square number, our value of x is root k wouldn't necessarily work, but it gives a rough idea of why we'll want to take something approximately equal to the square root of k within this method. Should give us a decent number of markings that should be about as small as possible. So actually, when k isn't a square number, all we're going to do is choose now n is, instead of being the square root of k, we'll take it to be the floor function of the square root of k. So you'll see that this isn't going to make too much of a difference, and you could just picture this, it'll be pretty close to our minimum. Maybe the ceiling function, the next number up, might be slightly better, but just in terms of finding a reasonable estimate for the number of markings we need to be able to measure k distances on a ruler, this is going to be good enough for our purposes and give us a decent upper bound. So here we'll take n to be, essentially if the square root of k isn't an integer, we'll just round this down, and we'll take this to be our number of initial markings, then we go up in our n times tables like this until we get up to our value of k. You can see there's also going to be some problems if this value doesn't actually divide into our value of k, so if it's not a factor of k. So there's a little bit more nuance to be explored now before we can try to turn this into a real upper bound for our general problem, see how many markings we can use. So now if we want to be able to measure all the distances from 1 up to some integer k, we're going to try splitting this up into blocks of size n like before, where n is going to be the floor function of root k. So the first case we'll consider is where n is actually a factor of k, because this turns out to be slightly nicer like we've seen before. So we'll call this case 1, we'll say that k is equal to q, some integer, times n, so that n is a factor of k. So we'll split this up like before, we'll have 0, 1, all the way up to n minus 2, n minus 1. We'll skip n like we were able to before, we'll go to 2n, 3n, all the way up to q minus 1 times n, and finally q times n. So you'll notice here that qn is actually just equal to k, so we can definitely measure all the way from 0 up to k. And this works just like before. You can measure anything from 1 up to n minus 1 starting from 0. You can measure n, for example, going between 2n and 3n. You can see we will be able to do this so long as q is bigger than 2. So here we are going to exclude 1 or 2 cases. If q is bigger than 2, we'll be able to do this trick of getting rid of n and going between 2n and 3n. And you can see because n is roughly the square root of k and q times n is k, so q must also be roughly the square root of k. We're only really restricting some very small values of k. So here you can actually check we're just excluding possibilities where k is 5 or below, so that we can skip the value n there. So then we can measure everything from 1 up to n minus 1. We can measure n going between 2n and 3n. Then we can measure everything from n plus 1 to 2n going backwards from 2n. Then we can measure anything from 2n plus 1 up to 3n measuring backwards from 3n, and so on all the way up until we get to qn, which will allow us to fill in all of those measurements all the way up to k, which is equal to qn here. So how many markings have we actually got? We've got here going from 0 up to n minus 1 gives us n markings. Then here we've got 2n, 3n, all the way up to q times n. So you can see this is just going to be q minus 1 markings. So in total we've got n plus q minus 1 for our number of markings that we need following this method to be able to measure all the distances from 1 to k, so long as we're in this situation where n is a factor of k. So if n isn't a factor of k, we'll write this as case 2 where k is q times n plus a remainder term. So this is essentially the remainder we get when we divide k by n. So here we'll have 1 between less than or equal to r, and r has got to be strictly less than n. So this is our second case now. And in this second case, we start just like before, 0, 1, up to n minus 2, n minus 1. We'll assume again that q is bigger than 2 so that we can skip n. So we go all the way up to 2n, 3n, and so on up to q minus 1 times n. We get up to qn, and we've seen, just like before, we can definitely measure all the distances from 1 up to qn here. So now we just need to be able to measure qn plus 1, qn plus 2, and so on, all the way up to qn plus r, which is our value of k. So I'm actually just going to add in qn plus r, which, just like before, this is equal to k. So you can definitely get k by doing from qn plus r back to 0. And then we can get anything in between as well. So we can definitely measure from 0 up to qn like before. And if we want qn plus 1, this is going to be equal to qn plus r minus, then to turn this into a 1, we just minus r minus 1. And here, because r is greater than or equal to 1, we can definitely do this. And we need to go all the way up to qn plus r, so we can keep going like this. We do qn plus r minus, this would be r minus r like this, so we get qn plus r minus 0, measuring from qn plus r down to 0. So we do fill in all of the remaining gaps there from qn onwards. We get qn plus 1 going from qn plus r down to some value r minus 1, and so on until we get, so this is minus r minus 1. To get qn plus 2, we take away r minus 2, and so on until we get to qn plus r. We just go all the way from qn plus r down to 0. So how many markings has this taken? Well, we've gone from 0 to n minus 1, so we've got n again in the beginning, then we go 2n all the way up to qn, which gives us q plus minus 1, but then we add an extra one here, so it's actually just n plus q markings. So we can see in either of these cases, first of all, we had n plus q minus 1 markings, but then in the second case, it's only actually one more, so we can do this with n plus q. So this gives us an upper bound now, n plus q. We can always measure any distance between 1 and k using n plus q markings, following this method. And now we want to turn this upper bound n plus q into a function of k, so that if we want to be able to measure all the distances from 1 up to k, we know as a function of k roughly how many markings we can do this with following this method. So first of all, we can get a nice upper bound on n, just because n is the floor function of root k. So we get for free that n is less than or equal to root k, because root k would round down to n, so n has got to be less than or equal to this. And you'll also see that root k has got to be strictly less than n plus 1, because otherwise, if it was greater than or equal to n plus 1, it would round down to n plus 1. We can just illustrate this with a numerical example. So let's say k was 7, this would round down to 2, and it's strictly less than 3, just to illustrate why we're strictly between n and n plus 1 like this, but we could be equal to n. And now to get our upper bound on q, it helps first of all just to square everything in this inequality. So we get n squared is less than or equal to k is strictly less than n plus 1 all squared, which gives us n squared plus 2n plus 1. And now if we want to get an upper bound on the value of q, you'll actually see that here k is supposed to be q times n plus some small remainder term. So here, just seeing that k has got to be less than n squared plus 2n plus 1, you can think of this n squared plus 2n as being n times n plus 2, like this. Then we've got a plus 1. So you can see actually, because k is less than this, you'll see that q should really be less than or equal to n plus 2, intuitively. And just to prove this, we could try, what if q was equal to n plus 3, or something even bigger perhaps? Then we would have k is equal to qn plus r, and q is equal to n plus 3, so n plus 3 times n gives us n squared plus 3n plus r, and r is just our remainder term. This is greater than or equal to 0, so this is greater than or equal to n squared plus 3n. And I'll write n squared plus 3n now as n squared plus 2n plus another n. I'm writing it this weird way now just so that we can compare it more easily with n squared plus 2n plus 1. And we know for sure n has got to be greater than or equal to 1, so then all of this is greater than or equal to n squared plus 2n plus 1, because n is greater than or equal to 1. But now we've run into a problem, because k is greater than or equal to n squared plus 2n plus 1. But we saw earlier that k has got to be strictly less than n squared plus 2n plus 1. So then we get a contradiction, and we can see that q can't be equal to n plus 3. And actually, if we were to make q bigger, for example n plus 4, n plus 5, you'd see that this would make the argument even worse here, and it would also contradict our assumption that k has got to be less than n squared plus 2n plus 1. So we can actually say not just q isn't equal to n plus 3, but q has got to be less than n plus 3, and because it's an integer, it's got to be less than or equal to n plus 2 then. So we can start to combine all of this together to get a single upper bound in terms of k on our value of n plus q, which is our number of markings. So n plus q, first of all, we know q is less than or equal to n plus 2, so this is less than or equal to 2n plus 2, so you've got n plus another n plus 2, and we also know that n is less than or equal to the square root of k, so this is less than or equal to 2 root k plus 2. So we get this then as our upper bound. Given any value of k, we can always measure all the distances from 1 to k using at most 2 root k plus 2 markings. And now we'll finish by looking at how close to optimal our solution is. So if you imagine we've got a fixed number of markings, let's say we've got m markings, and we want to know what is the maximum number of distances that we could measure using this many markings. So if we just look at a quick example, you see that the number of distances you can measure with a certain number of markings is limited by the number of pairs of marks that there are. So here, the number of pairs we've got is 3. And more generally speaking, the number of pairs of markings, which will give us the number of distances we could possibly measure, is just going to be m choose 2. So we see then that the total number of distances you could measure, our value of k, has got to be less than or equal to m choose 2. And m choose 2 we can just write as m times m minus 1 all over 2, like this. So then we can rearrange this inequality and we'll get now a lower bound on the number of markings that we need. So here we can multiply by 2 on both sides. We get 2k is less than or equal to m times m minus 1, or m squared minus m if we expand. And if we want to make m the subject of this, we'll complete the square. So we get m minus a half all squared minus a quarter, like this, is now greater than or equal to 2k. And if we add a quarter and we'll take square roots on both sides, we get 2k plus a quarter has got to be less than or equal to the square root of m minus a half all squared. So we get m minus a half because this is going to be the positive root, because m is greater than a half here. So then we can just add a half to both sides. We get m is greater than or equal to root 2k plus a quarter, all in the square root, plus a half. And then just so that we get a slightly nicer looking lower bound here, you can see 2k plus a quarter in the square root. We could just replace this by the square root of 2k to get a slightly lower bound. And here this plus a half, we can just get rid of this as well. So this is all greater than or equal to the square root of 2 times k. So this gives us quite a neat lower bound then. We've got root 2k, which I'll write as root 2 times root k, is less than or equal to the number of markings that we'll use here. And we've seen before that our total number of markings can be done with 2 root k plus 2. So we can actually do this with less than or equal to 2 root k plus 2 markings. So you'll see here we did this with 2 root k plus 2, and our theoretical lower bound for our number of markings is around root 2 times root k. So here we're only actually root 2 times bigger than our theoretical lower bound, which is quite good that we're not an order of magnitude bigger, we're actually just a constant term bigger. So root 2, we're about 1.4 times bigger than our theoretical lower bound, which I think is quite good considering how simple and elegant our setup was for measuring all of these distances from 1 up to k.